So this session is on why do we do proofs? And let me just make this full screen for you. Let me start by saying that there are a few questions that may have occurred to you when it comes to proof. Here are some of the ones that I've heard or come up with. Why do we have to do proofs at all? One reason, isn't everything either obviously true or obviously false? I'm going to show you some examples today which I hope will convince you that things are sometimes neither obviously true nor obviously false. So again, a lot of people wonder why you should prove anything at all. I'm hoping to give you some motivation for that today. This is some motivation. How can you ever be absolutely sure whether something is true or false? Couldn't there be some special case you've missed? Well, if you've got a proof that you're absolutely sure covers every case, that's a pretty convincing way to help you be sure that something is really true. What about if something is intuitively obvious? You've got a pretty good idea what a continuous function is. What about this intermediate value theorem that a continuous function can't jump over some value? If a continuous function defined at an interval takes a couple of values, it must take every value in between. Why should you have to prove a statement like that? Because it's intuitively obvious. You couldn't possibly miss anything out when you join the 2 points on the graph. Well, I'll have something to say about that, and there'll be more as we go through the module mathematical analysis. Why are definitions important? Why do we need to know what our definitions are? We're going to see that if you don't know what your definitions are exactly, you haven't got much chance of figuring out what the right answer is. In fact, the answers usually depend on the definitions you're working with, and knowing roughly what something means is not going to be enough. And do you need to memorize a lot of proofs? Well, I do hope not. I don't think memorization of proofs, line by line, memorizing every step in them, is a very constructive activity. I've said something about this before in the introductory session. What I think you need to do is understand how to do proofs. You need to be able to understand how to do the routine parts of proofs. And then all you need to know is the unusual ideas, those particular tricks that you wouldn't have thought of for yourself. And there's far fewer of those than there are routine types of proof, at least in the modules I'm going to be teaching in second year. Perhaps in more advanced modules, you need more ideas. But in the proofs in second year modules, there aren't so many ideas. It's mostly automatic proof with a few interesting ideas that you really need to know. So I'm going to give you a few problems to think about today, which will hopefully motivate why we do proofs. And this is going to be the first problem, and in a bit I'm going to give you a bit of time to think about it. So the question is, for which prime numbers p, if any, is p plus 1 a perfect square, which means it's a square of an integer, or the square of a non-negative integer if you like, because that doesn't change the answer. Because if you square a negative integer, you get the same answer as squaring the corresponding positive integer. Well, it won't take you long to find one example, and then you might try to find some others, and maybe you'll have a bit of difficulty, and then you might wonder if there are any others, and then if you think there aren't any others, you might want to try and prove that there aren't any others. So what I'm going to do is I'm going to give you a few minutes to talk to each other. Think about this problem. You should quite quickly find one example, but the question is, are there any others, apart from the obvious example? And if not, can you prove it? And so what I'll do is I'll pause the recording there, and I'll give you a few minutes to think about it. Okay, so let's find out how people have got on with that. Let's pick up my comments document. I'm pretty sure everybody found out that 3 works. So this is the p plus 1 a perfect square. P equals 3 works. This is problem 1, of course. Because 3 plus 1 equals 2 squared. So, can I have a show of hands, probably not to pick on anyone, as usual. A show of hands, who thinks that that's probably the only one? And who thinks there might be another one somewhere, they just haven't found it yet? Okay? And until you've found a proof, that's a perfectly reasonable thing to believe. And until you've got some reasoning, until you've come up with some reason for deciding what the answer is, you should be equally biased either way, because checking a few cases is not going to help you with this problem. Okay, so the question is this the only one? Does anybody think they've got a proof or some reason or an explanation why 3 might be the only one? Any suggestions? Yeah?
If you let p equal n squared minus 1.
Okay, so that's a very good idea. We're going to do some. We're going to rewrite it. So the claim is 3 is the only prime p that works. So we're going to claim that 3 is the only prime p such that p plus 1 is a perfect square. So suppose p plus 1 is, I think you went for n, is that right? N squared. In this case, p is n squared minus 1. Right, so what do you do with that?
So n squared minus 1 is n plus 1 times n minus 1.
Good, so you're factorising it and writing it as n plus 1 times n minus 1. That's very good.
The only value of p apart from 3, n plus 1 and n minus 1 would both be factors of p which aren't p or 1, so that wouldn't be a prime number.
Okay, so you're going to argue that 3 is the only one that works because these factors can't both be sort of genuine factors. You've mentioned p and 1. There is one other possibility that could occur because you're looking for, I think, non-negative factors there. So as well as p and 1, if you've got a prime number, there's a couple of other factors that there might be, which could be, we could have factors of minus p and minus 1 as well. So you have to watch out for the cases where these factors could be plus or minus 1. And that's the only ones that could possibly work. But otherwise, you got it, right? So you're saying one of those factors must be 1, and I just say that the little rider, maybe one of those factors could be minus 1, and the other one minus p, though that's quite unlikely. You could eliminate that quite quickly. But certainly only a very few possible cases. So, since p is prime, at least one of these factors must be plus or minus 1. And you actually find you can get n equals minus 2 and n equals 2. N equals minus 2 will give you the minus 1 times minus 3, and n equals 2 will give you the 3 times 1. So you check all cases, and you find that n equals plus or minus 2 are the only possibilities that work. Giving p equals 3 again. And n equals 0 doesn't work, for example. So nothing else works. I'll leave it as an exercise for you to generalize that result in any way you can think. Right, so let me go back to the presentation. Anybody got any questions on that argument? What went on in that proof, actually, let me say, is, in a way, you discovered that what you were trying to do was sort of back to front. Writing it as p equals n squared minus 1 tells you everything that's going on in this problem, whereas p plus 1 equals n squared looks a bit more mysterious. So simply rearranging the equation, reposing the problem, sort of recasting it, and you immediately see that it's a factorization problem. Right, let's bring that back up to full screen. Well, some of them aren't as easy as that. Fermat's last theorem. Is it possible to have x to the n plus y to the n equals z to the n? Well, yes. If n equals 1, it's very easy to get equality using all sorts of x, y, and z. If n equals 2, you can have 3 squared plus 4 squared equals 5 squared. Once n reaches 3, it seems to be rather harder. And then you look at any n bigger than 2, and it does seem to be rather hard if you're assuming that x, y, and z are strictly positive. 0, of course, would be far too easy. Well, turns out that it can't be done for any value of n bigger than 2 with positive x, y, and z integers, but it took 350 years to prove it, in spite of the fact that Fermat claimed that he had an elegant proof that was just too long to fit in the margin of the book that he was reading at the time, and it stumped people for 350 years, and goodness knows how much background you need to understand the full proof that it is now, because it uses so many advanced tools from number theory. But if you want to find out about Fermat's last theorem, well, you can read the book. So that, I hope, handled why aren't things obviously true or obviously false. But here's something else. This one is supposed to be relevant to the question about why do we have to bother proving intuitively obvious facts. This is something called Simpsons Paradox, and it's not a trick question. And if you look up Simpsons Paradox on Wikipedia, you'll find a whole load of fantastic examples there. So look up Simpsons Paradox on Wikipedia, and you'll find that there have even been legal cases based on this. So this is not just an abstract mathematical phenomenon. It really has come up, and it's upset a lot of people. So you've got these two hospitals, Hospital A and Hospital B. Hospital A says, we cured a bigger percentage of our male patients last year and a big percentage of our female patients last year of this particular disease. And Hospital B says, well, that may be true, but we cured a higher percentage of our patients than you did. So, not a trick question. Both hospitals had some men and some women, non-zero numbers, visiting with this condition and treated them. everybody you visited was either a man or a woman. So no trick answers, no trick question. Given that none of the numbers involved are 0, is this actually possible? Must one of the hospitals have made a mistake? If it is possible, which hospital would you rather be treated by? So what I'm going to do is I'm going to give you a few minutes to think about this, try a few numbers out, see if you can find the numbers that work, or else try to prove it's impossible because intuitively this doesn't seem very fair. Try to come up with a view as to whether you think it might be possible. If you think it might be possible, try to find some numbers that work. If you're going to try numbers, try not to make them too balanced. Make sure that you don't have the same number of each kind of patient visiting both hospitals, because that would make it much too easy. Okay, so I'm going to pause the recording there and give you a few minutes to think about this problem. So now you've had a little while to think about that one. Let's see what people come up with. So the problem of 2 hospitals. Let me start by, again, promising not to pick on anyone. Can I have a show of hands for those who think that this isn't possible? Can't be done. Okay, we've got a small number. Can I have a show of hands for people who think that it probably is possible? Okay, so more of you think it probably is possible. Okay, and now I want to ask, I remove my promise not to pick on anyone. No. Is there anyone who's come up with some numbers that they think work? I see we've got a choice or two. I'll tell you what have you got? I haven't got a calculator, so I may not be able to check your percentages as easily. I hope somebody's got a calculator. Okay, so let's have a look. So let me make a little table here, or possibly a big table. So we've got hospital A and hospital B we want, and the male's cured and the female's cured. Oh, that's not very good. Get rid of that. In the form of A over B, I think you're going to give it me. Okay, so you've got 1 out of 1, is that right, for hospital A? Yeah. For males, okay. So 1 male patient turned up and got cured, that's 100%. Hospital B? 99 out of 100, okay. We've got 99%. Now what I'm going to do for the female patients? 2 out of 3. That's a good one. That's 67%-ish. One out of 2 for 50%. And let's have a look at what happens for all patients. We got 3 out of 4. Is that right? 75%? But over here, we've got 100 out of 102. I don't know how many percent that is, but it's about 98%. Anybody got an exact number? It's a lot, anyway. So B's done better on the overall patient percentage. A did better on both the males cured and the females cured. So it just goes to show that you can always lie with statistics. But actually, I have no idea under these circumstances which hospital I'd want to go to, because either the numbers are too small for hospital A to be sure of what's going on at all, and so on. But in the examples on Wikipedia, the Wikipedia Simpsons Paradox page has got some explanations as to how you can actually decide what's really going on. Sometimes there is what they call a hidden variable, or a sort of lurking variable that you don't know about, that actually explains what's going on with the figures. And it often is the overall one that's wrong, and the one that's better on the specific issues that's right. And you have to look at the Wikipedia page for a bit more of that one. So if you've got Simpsons Paradox on Wikipedia, there's loads of interesting examples and information about legal cases and how they were resolved, and all sorts of interesting things like people complaining in the States about whether colleges were being biased against females in their admissions procedures. And exactly this paradox came up, and people had to argue whether it was whether people were being unfair or not, and a whole load of maths had to be done. Right, let's get back to the main presentation. We'll go back to full view again. And we move on to the bit about definitions. Now, if you don't know what definitions you're working with, I claim it may well affect whether or not you can figure out what the answer is. And indeed, different people with different definitions will get different answers. And here are some problems especially chosen so that you might disagree with each other. Though it is possible that boringly everyone will agree about the answers to these. So here's some questions which I'm going to give you another chance to think about, and then we'll get some feedback on who thinks what. I'll show you them all. Problem 4, are squares rectangles? Is every square a rectangle? Are rectangles allowed to be squares? Are equilateral triangles isosceles? So is every equilateral triangle isosceles? Is an isosceles triangle allowed to be an equilateral triangle? And 3 numbers, which you have to figure out whether or not they're prime. This is an unfair question, by the way, but I'll be interested to see what people think. So the question is phrased as, which of the following numbers are prime? I think the answer could be different if I said, which of the following are prime numbers? Strangely enough. Anyway, part A, well, here the numbers are 2, 1, and -3. And so I'll give you a few minutes to think about those. And again, I'll pause the recording. I'll come round and see what people are doing. Okay, so let's start with problem 4. Can we have a show of hands for who thinks that squares are rectangles? That's a lot of people. And who says that squares are not rectangles? A small number of people. Okay, well, it depends on the definition you're using. Most mathematicians these days, but not necessarily in history, would say that a square is a special kind of rectangle. But that's just what the convention is these days, and historically, the convention may well have been something else. And let me ask you this. Suppose a child in primary school is shown a few shapes and said, which of these is a square and which of these is a rectangle? And suppose they point at the square and say, this is a rectangle. Do you think the teacher's going to tell them they're right or that they're wrong? I think the teacher's going to say, no, that's the square. This other one's the rectangle. So perhaps the answers have changed for you since primary school. Problem 5 is almost exactly the same. It's the same problem you have to deal with. What is the definition of an isosceles triangle? Now, Wikipedia says that an isosceles triangle, well, the last time I looked, Wikipedia said that an isosceles triangle is a triangle with two equal sides. But it doesn't make it clear whether it means exactly two equal sides or at least two equal sides. It then goes on to say that equilateral triangles are a special kind of isosceles triangle, which would contradict it if it had meant that it has exactly two equal sides. So if you say it has two equal sides, isn't that ambiguous? It is to me. So you have to make a decision again as to whether you're going to allow three equal sides. And again, the mathematician's convention at the moment is that equilateral triangles count as special kinds of isosceles triangles. But historically, that may have gone the other way. When they were first introduced, if you go back to Euclid, I think you may find the answer is different. I'll refer to experts in mathematical history to clear that one up. Problem 6, as I said, is unfair the way it's asked, but it should reveal to you that you've got to be very careful about thinking what definition of prime you're working with. I'll assume that everyone agrees that 2 is prime, though I will point out that 2 is equal to minus 2 times minus 1, and so if your definition of prime makes minus 2 times minus 1 equals 2 a problem, then you may want to change your definition of prime. Because I think everyone agrees that 2 is a prime number, and so you better come up with a definition of prime that allows that. Mathematicians insist that 1 is not a prime number, so whatever definition of prime you're using, you better make sure that 1 doesn't satisfy it. And then we come on to the tricky issue of the number minus 3. Kind of a show of hands for who believes that minus 3 is a prime number. It's a small number. Let me ask you, how many of you believe that minus 3 is prime? Slightly more. I go along with there being slightly more on that one. And who believes that minus 3 is not prime? A small number of people. And who believes that minus 3 is not a prime number? Yes, I know it sounds like I'm asking the same thing twice, but there is a reason why I've asked it those two different ways. And I'll explain that now. The answer is both yes and no, depending on which convention you work with and which definition you work with, even for mathematicians. So what's going on here? Well, there's an official notion of prime number. The prime numbers are well known to be 2, 3, 5, 7, and so on, not including 9. And everybody knows those are the prime numbers, and those are generally agreed by the mathematicians to be the prime numbers. So the term the prime numbers is reserved for those special, strictly positive integers which have some rather nice properties which define being prime. However, those of you doing algebra and number theory are presumably meeting rings at some point, abstract rings, and in an abstract ring, there is a notion of a prime element. Now, you may not meet a prime element this year. You're more likely to meet something called a prime ideal. But there is a notion of something called a prime element in a ring. And that notion of prime can't tell the difference between an element and its negative. So if you're asking, is minus 3 a prime element of the ring of integers, the answer, according to mathematical definitions, is yes. So in other words, minus 3 is prime as an element of the integers. It's not prime in the sense that it's not officially a prime number. And so this time you've got problems because the two different conventions disagree. Any questions about what we've been talking about today so far? Well, I hope that I have managed to convince you that definitions are important and that proofs are well, I hope I managed to motivate the need for proofs and the fact that things that look obvious might not be true and that you've got to be careful, and that proofs can often show you why something is really true. And so I hope I've managed to convince you that proofs are generally a good thing. And I'll stop the recording there.